Went ahead and started the live stream just in case. Let me hit pause on this video here. Just a sec. We're getting people in here. All right, so now I won't forget to do that. Thanks. Okay, so we got that going, and I don't know where we're at here. There we go. All right, so I think I hit everybody to get him in here. All right, so today we're going to talk about potential energy graphs and force graphs. We alluded to this last time. I showed a simulation right at the end. Maybe you remember with the two atoms, and there were those curvy plots and things. So I want to kind of go into that in detail today and do some worked examples. That particular information, I think you have a group activity coming on Wednesday, and it's going to relate to kind of a little bit of all of this stuff blobbed together. Like there were energy problems with springs, and we could talk about plots and all kinds of stuff. So it's kind of a whole chapter group activity on Wednesday. So that said, I might mention something else just as a side note here, just because I happen to have it up. You might get a kick out of this. This is totally unrelated to the rest of the class today, but I just wanted to show you. I know we're going to start coding this week, and there's probably a lot of apprehension for many students because you've never coded in your life. But I was explaining this to my 8-year-old daughters, and they were getting it. And the idea is this is the guts of your computer code. If you think about this, this is pretty amazing when you think about what we could do these days with computers. We know F equals ma. A is delta V over delta T, and V is change in position over change in time, right? Well, the idea is you could rework these equations in coding. You could solve for the acceleration by taking a force and dividing by mass. Force is a vector. We're going to talk about how to handle the vectors in the code this Thursday. And then it turns out this is the equivalent of number 2, which in a coding statement says V plus equals A times delta T. This is the way you get from an initial velocity to a velocity a short time later. And once you update the velocity, you could do the same thing with the position. And lo and behold, you could be making computer animations, making these graphs and et cetera. Obviously, if you have a position versus time graph and velocity versus time graph, you could make all that information in your own simulation after, if not this Thursday's lab, then by the next one. So we're going to take some time to dig through this. So you don't need to be scared about the coding. I know you can do it. All right, that's I don't know. I'm kind of excited to get you into that because I think if you give it a chance, it may change your outlook on some of this stuff. So fingers crossed. That said, let's go into chapter 8. And let me give you a page number so you have something to start with. I think last time we left off right about here. Let's look at, go to page 22 and 23. You could open up to page 22 and 23, and I'll do a screen share as well. All right. Okay. Move some windows around here. All right. So in case you forget some of the stuff we talked about last time, it's right here on page 22. I don't want to spend a lot of time going through this. The main thing that I want to remind you of is f sub x is the opposite of the slope. And if the slope is 0, that means you're in equilibrium, right? Equilibrium means no force. And we classified these. And remember, this marble analogy is hugely useful. All right. A note on the units. If you forget the units, nanometers is 10 to the minus 9th meters. I remember it as nano, but most of you don't know the TV show Mork and Mindy, so that reference is lost on you. But Robin Williams did go to Allen Hancock College. Anyways, here we go. We've got milli EV. So 1 EV is, well, let me put it this way. 1 EV is 10 to the minus 19th joule. So that's a unit of energy. So I'm going to use these units because these types of units are very common in these types of problems. So why don't we use the right units that are common to these in real life situations? This is for, nanometer scale is like atomic scale. So we're thinking about atomic scale situations. All right. Anyways, why? Because a lot of this stuff is used in these subjects: chemistry, physics, quantum mechanics, and electrical engineering. All right. There's your picture. Stable is the bottom of a well, unstable is the top, and neutral is flat for a long ways. Okay. Let's look at page 23 now, and that's the correct spelling for the Leonard Jones potential. This is some crazy potential function. So let's say we know the potential function. It models the interaction between two atoms. If you care, the 12th power term is Pauli repulsion. 6th power term is attractive van der Waals. If you don't know what they are, take a chemistry class. We're going to assume that this is a lowercase sigma, right? It's not the cherry bomb delta. And this is epsilon, okay? So those are sigma and epsilon. There's different ways you could write those symbols. Let's worry about that later. They're positive constants. X is horizontal position. And then the units are discussed in part A. So, all right, we're going to leave off units for the rest of the page. But before we do that, let's figure out the units on sigma and epsilon, okay? So when you look at this crazy equation, we need to figure out the units. Where would you start in figuring out the units on that beast? Would you start with trying to figure out the units for sigma, or start with trying to figure out the units for epsilon? Which looks easier?
Sigma.
Sigma. Okay. So where are you going to go with that? How would you try to figure it out? It's tricky, isn't it?
Yeah.
Well, let me ask you this. How about we start with this term inside the parentheses? I agree with you. I claim we can tell something about the units of this. Well, what should be true about these two terms if we're subtracting them? If you're subtracting them, what has to be true?
They both have to be the same units.
Okay, so now you're telling me that something to the 12th minus the same something to the 6th has to have the same units. What is the only possible unit it could have?
No units.
No units to the 6th is equal to no units to the 12th. Any other unit doesn't make sense. So that said, what does that tell us the units of sigma are? Look at this thing right here. We know this has
same as X.
Same as X, which is meters. Now you might be saying, wait, shouldn't I say nanometers? Remember that meters, nanometers, those are the same units, units of length. All right. So now that we know that, what are the units of epsilon?
Just whatever the units of epsilon are.
Okay. Well, what are the units on this side? U is a unit of force, velocity, position. What is it?
Is it velocity?
Nope.
It's joules.
Joules. So what are the units on E? Or sorry, epsilon?
So joules times meters?
Nope. Joules.
Just joules.
Look inside. Sigma over X, that has no units. So everything inside of here has no units.
Okay.
Right? So there's nothing there. So epsilon has to have the same units. And it looks like an E. So that's yeah. Obviously, it's better to just tell you the units, but I thought this was a fun, challenging unit question. This is about as hard as unit questions get. I hope you agree with that. But so the units here, sigma is a length. It's the characteristic length. And epsilon is like this energy unit. So, okay, so we've got these. Got it. That's the units. Normally, I would just tell you in a test question, but here it's worth struggling through that one. All right. It says determine the force associated with this potential energy. To be clear, that's the force that one atom exerts on another. How do you get force from you? What do we do? Do you remember?
Was antiderivative slope, or I should say the inverse or the slope, but negatively.
Okay, yeah, something like that. Let
Yeah.
me write this up. Delta U was minus the integral of f sub x dx. This came from the definition. And then, so the opposite of that is f of x is, you said minus the slope, right?
Yeah.
What's a way to write that mathematically?
Would be negative dx or d over
Yeah.
dx.
Yeah, negative d dx of u. Sweet. So this, take a second and try to take the derivative of that, and don't forget that frickin' minus sign. It's like so easy to forget because you spend all this time understanding the concepts and then you miss one minus sign and you miss a point. It's very frustrating, I know. Watch out for that minus sign right there. Okay. Take a second to take that derivative and see what you get. Okay. I'll go ahead and pop it up on the screen here. Let me write it down. We got u of x is equal to some, oh, and I better write the problem number, 8.24. All right. So now what I would do is I would say f sub x equals, I know there's a derivative, and I'm going to put that minus sign in bold red so I don't forget it, because that's the thing that we all forget sometimes, right? That's where the marble analogy will come in handy for checking your work. You'll see in a minute. It's really easy to forget this. That's where the marble analogy helps. So, well, the 4 epsilon pops out. I'll just do that. This is the other way. So you've seen this is one way to write epsilon. The other way that people get lazy, it looks like a C with a line through it. Those are both ways of writing epsilon. Okay. So maybe I'll write it like this. Sigma to the 12th, x to the negative 12th. Ooh, I forgot my derivative. Sorry about that. d dx. And then rather than try and do it all in my head, I'll say this is sigma to the 12th, x to the negative 12th, minus sigma to the 6th, x to the negative 6th, just so it's easier for me to see that power rule. So f sub x equals, don't want to forget this minus sitting out front. Okay, now when I take the derivative, I should get negative 12 sigma to the 12th, x to the negative what? 13? Okay, and then for the next term, I get minus negative 6. Oh my gosh. Sigma to the 6th, x to the negative 7, I think. Double check my work there. Let me get this glare. All right. And notice, you don't have to do it the same way as me. You could plug this into Wolfram Alpha to check your work as well, obviously, especially in online mode. And I recommend that even if we weren't in online mode. But here's the deal. Writing out each term so that you make sure you get the minus signs right is what I'm trying to do here. Because I've been doing this 20 years and I still screw up the minus signs sometimes, right? So taking the time, I like to say, let the paper do the work. Meaning, instead of trying to do it all in your head, you're not stupid, but by writing it on a paper, you're just less likely to make mistakes. So take the time to write it out, get those, like here, I'm like, oh, minus, and then a minus. Obviously, I could have fixed that in my head, but it just starts to get burdensome to try and remember every detail in your head after a while. So whatever works for you, like, oh man, now I got this minus sign out front. So what I might do is clear up this one with these. And so now I'm like, okay, I'll keep that one and get rid of it, right? There's many different ways to do it. So, all right. So then I think at this point, we've got it all. And I think that's the crux of it that I wanted to show you. Let's go to the solution now and see if there's anything special in there. All right. And hopefully I didn't make a typo live, but let's see. What is this? 8.24. Oops. Let me move this here. Let me hit Control F, 8.24. There we go. Okay, so it looks like you get something that looks like this crazy mess. So, I factored out a 6. I see what I did. Yeah, so we'll get to 24. We got it. So from there, I think the answer makes sense. And notice I brought these powers back down. Of interest, we see that the smaller power term is negative. Let's think about this force equation really quick, right? And let me get it back up here. Let me just write that so I don't waste time. And I want you to think about which term should dominate when x is small. Which term should dominate when x is small? I'm going to get the equation written up and we'll discuss in a second. So think to yourself. Okay, I've got it now. Okay, so this is what I got for that. Sorry, there's just a little glare there. Okay, so in this case, which of these two terms is going to dominate when x is a small number? What do you think?
The one on the right?
Okay, so here's what we could do. Just pretend everything else in here is the number 1. And let's say you put in 0.1 for this one and 0.1 for that one. 0.1 to the 7th. Okay, 1 over 0.1 to the 7th would be about 10 million. 1 over 0.1 to the 13th would be, what is that?
Bigger.
10 trillion. Yeah, bigger. So this one. So basically, if you have a power in the numerator, generally speaking, the smaller power will dominate at small x. If you have negative exponents or x in the basement, the smaller it is, the more that power helps out. So in this case, we see the following. At very small values of x, this is negligible. We just saw it's like a million times, literally a million times smaller. Actually, 2 million times smaller. Well, it depends on what sigma is, I guess. But yeah, we would expect it to be a lot smaller. So in this case, when you're at very small values of x, the force is positive. However, when you get to large values of x, when x is bigger than sigma, then this term is going to dominate. So we see that there's a trade-off, and now we understand the physical meaning of what this sigma parameter is. It's the spot where things transition from pushing away to pulling towards, or something related to that. There's a 2 in there. There's some powers. Let's see that. So that's what the next question is. If I could go back to it, and you could chime in at any time with questions here. That was this piece of information. Oh, let me see here. Okay, there we go. So equilibrium positions. I don't know if you saw that already. Whoops, I just broke this whiteboard. Let's fix that really quick. What did I do there? I don't know. All right, fix it later. All right, how do I get the equilibrium position, everybody?
That's when the derivative is 0, right?
That's right, or set the force equal to 0. So if you set the force equal to 0 and solve for what? Equilibrium position means solve for what variable?
For x.
Exactly. Perfect. So when we do that, let's go over here and take a look. So set f of x to 0. Remember, f of x is the derivative. And so I found this unusual result. It's about 1.12 sigma. So remember when I was saying sigma is kind of like the trade-off? Well, you get a factor of 2 to the 1/6 in there as well. Whatever. So now Oh, well, I guess I've kind of spoiled the answer there since I say it. But right here, which graph is f of x and which is u of x? So if I scroll down here, I hope you agree that x is all on the horizontal axis for both of these. So this is x on this axis. And what we're told here is this is u and this is f sub x. And the idea here is, look at this spot right here. I see the slope equals 0 right there. And notice the force is equal to 0. And notice that's at x equals 1.12. So this is x in units of sigma, if you will. I don't really care about the units on this particular one. We're going to do all the units and stuff on the next example. So for now, let's just get used to the big concept. I could identify that the slope is 0 here, which corresponds to this position here. And that's how I could tell which graph is which. Notice the slope is 0 here. That does not correspond to 0 in the other one. Clearly, that relationship isn't working. So it must be the other way. This is the upper graph is u versus x. The lower graph is f versus x. All right, that's all there was on that. Okay, and then so let's kind of get this concept here. So right here, if we're comparing the slope, let's just start here. Right here, I have a large negative slope. That corresponds to a huge positive force, right? And notice right here, I still have a large positive slope only until about right here. We see that all these values until this point have, large negative slopes. So these have negative slopes here. Again, I'm sorry if I said it backwards. We have a negative slope. And remember that f sub x is equal to negative the slope. So that's why we get positive values up here, huge positive values. Over here, we already checked the equilibrium point when slope is 0, force is 0. And now we see small positive slope. We see small negative values for f. And while it's a little bit weird, there's a maximum force that occurs right here. I should say a maximum leftwards force. The maximum rightwards force goes to infinity. But you could actually figure out what position would cause the most leftward force by taking a derivative right there. Let's see that a little bit better if I scroll down. Right? So you could actually take a derivative of the force equation and set the force equation to 0 if you wanted to find this spot. That would give you the, the minimum force or the maximum force to the left, however you wanted to think about that. All right. So far, so good. I'll unmute at any time and ask questions about this stuff. I have no idea how well this is coming across on the internet. All right. Okay. And we're going to keep going. This is basically the same problem. Okay. So now think about this. If you placed a marble on the U-plot at x equals 1. So let's do that. So if we placed a marble on here at x equals 1, okay, which way would it roll? Would it roll towards the right side of the graph or towards the left side of the graph? It would roll this way, right? Notice the force is positive there. That's what that marble analogy is supposed to mean. So again, the marble released from rest would trend towards the right end of the graph. That means the force should be a positive value in the I-hat direction. Let's keep going. If you placed it at x equals 2, what would happen? Well, so now if we place it over here, it would tend to roll that way. Notice that's the same thing as having a negative force. Okay, so you would go towards the other way. And I guess I could say this. If you look at this, the force here should be a lot smaller. It's a very shallow slope. It's close to 0. Whereas the force over here was huge. All right. All right. Force here, huge and positive. Force here is small and negative. And then if you release this from rest, what would it do? It would bounce back and forth. And this is exactly what we saw in that animation last time. All right. Sorry, I'll keep going. All right. So, here's a deep thought. I guess there was no question there. So at the equilibrium point, I think we've already talked about that. I'm going to stop the screen share and say we've covered this here. That was this problem. That's our goal. We want to understand these plots conceptually. We want to know how to do the math. And then this completes chapter 8. So we've seen different types of problems in chapter 8. Some are where blocks are moving around, or two blocks and they're swinging, or hitting springs and there's friction. And we do that U initial plus K initial equals U final plus K final. And then there could be work external or non-conservative. Then we also see that you can relate potential energy to forces. And notice this ties that chapter in with the kinematics and all of that stuff. For example, right at the beginning, I was saying, well, you could use a force to get acceleration and use kinematics. Well, now we see that you could actually use an energy equation to get a force, to get acceleration, to do kinematics as well. So it's just all of these subjects are all interrelated, and you can go back and forth. If we know about kinematics, we could get the force and then do an integral to get the potential in certain cases. It's all related. I don't know. I think that's kind of cool. I hope you do too. All right. Okay, we've already mentioned this as well. Great. All right, let's do a problem with numbers and units and get this thing done. All right, so this is a great place to start. Okay. This is called a double well potential. This appears all the time in real life if you have two atoms trying to hang on to an electron, say, right? And you could imagine this might be the location of one nucleus. This might be the location of another nucleus. And the electron is kind of, sometimes it hangs out in here, but if it gets hit with enough thermal energy, it could pop over and hang out over here for a while and just go back and forth. And what's complicated is in quantum mechanics, it can actually tunnel through there. But so this is a realistic potential that we might encounter in a chemistry class or a real world problem sometime. Okay, that said, let's look at it. We've got a plot of U, and the units are in nanometers and EV. So this time I'm actually giving you the units. Okay, so take a second to look at this one and try it out, okay? Try not to look at the solution right away. I'm going to get it drawn up. Now that's going to take me forever. I'll make a rough graph. It won't be perfect. This is what, 26? Okay, 8.26. It's my attempt to draw that. And I'll write it up. Almost there. Okay, I think I got it. Okay, sorry, it's not a perfect picture. It's kind of a W looking thing, whatever. I think this goes more steeply up, right? Kind of goes up like this, like a rocket. Okay, so in this case, how many equilibrium points are there?
3.
3. All right, and so how many stable?
2.
2, that's the low points, right? That's where the ball will oscillate back and forth. And then there's one unstable in the middle. Got it. Okay. Now, what's the next part? I forgot to read the question. Let me read it. The next part says, get the force. How do I get the force?
Take the derivative
Nope.
or a negative
Right.
derivative.
All right. So I'm just trying to be, yeah, because we'll all do that where everybody forgets that minus sign once. Okay. That's what the homework's for. Minus the derivative. Okay. Of u of x. Okay. And so I bet you could take a derivative of this pretty quickly. The first term, we should get a -3 because there's a minus sign, and 4 times 3/4 is 3. Oh boy. And then 2 times this, what's that going to be? 7.5 and positive. And here that term would just drop out. So hopefully you agree the force is equal to, let me not screw this up now. Hopefully it's 3.00 x cubed with a negative, right? That one's got the negative. Negative. See what I just said about trying to do it in your head? Look how slow I am now. And then this one was what, plus 7.5? Telling you, getting used to writing it on paper, you'll just be faster and make fewer mistakes. So I'm going to highlight this just so it stands out. Negative on this one, positive on this one from this red minus sign here. Hopefully that's it. Hopefully I didn't make a mistake. Let me read the next part. Okay. Okay, so plug in some numbers. This would be a good time to use Excel, right? You just, I don't usually get on this side of the board. Hey, what's up, everybody? So determine the force at the, okay, so if you had an Excel spreadsheet, that would be the way to go, right? But if we just plugged in a few numbers, we could do this and make that sketch. And to be honest, I'm going to save us some time and look at the solution just because I know you could do that. You should do it. I'm cheating, but right. Let's see. There's that force plot. Okay. And so I got the equilibrium positions there. Great. Oh, there's the 3 equilibrium positions with extra sig figs. Notice it's easier to get extra sig figs by solving this equation. Ooh, that's kind of cool. All right. But look at that crazy force. We see as you get to large values of x, this term should dominate because again, the x cubed is in the numerator now. So small values of x, this term dominates. It looks linear at the origin, right? So look at this, 7.5. It should be linear approximately at the origin with slope 7.5. Ooh, this is kind of interesting. So if you move to the right, you get a force to the right and you get pushed farther away. That's unstable. That makes sense. Whereas if you're down here and you get pushed left or right, well, whoops, I should be careful. These wells are not located at the same as these other wells, right? Let me see if I can get this all on the screen at once. That's pretty close. All right, so if you look at these, notice the following. I tried to line these up. Apologies if I didn't. Let me get an annotation in here. That's supposed to be that equilibrium point. And I'm kind of drawing from an angle, so maybe it's not perfect. It's, oh, the graphs aren't perfectly lined up. But so those are those 2 equilibrium points. Sorry, the graphs aren't perfectly lined up. One of them looks a little, whatever, they're close. All right. So this starts to make sense. Okay, cool. Let's go back to the main picture. Or at least this is what I would expect. Maybe it doesn't make sense to you yet. Okay. What are the units of this force? Okay, remember, let's look at our equation right here. This force is units of, well, whatever I did here. It's du dx. What were the units of u?
We said EV, right?
EV. And what are the units of dx? It's an x.
So it's just meters.
Yeah, right. A small change in position must be in units of meters, just like position. So EV per meter. Well, wait a minute. Does anybody remember what an EV was equal to?
It's a joule. I just can't remember how small.
Yeah, I think this was actually nanometers, right? But it was 1.602 times 10 to the minus 19th joules all over 1 nanometer. So the units start to matter now, but I'll point out that a joule is essentially a Newton meter. And so we see, well, this is 10 to the minus 9th meters, and we get back units of newtons. They are newtons in this weird way. So the units of force are EV per nanometer, which are effectively the same thing as newtons if you put in this weird conversion factor. Cool with that? EV per nanometer relates to newtons. So at some point on some test, sometime in this class or the next class, you're going to be faced with one of these plots. I'm going to ask you to get the force, and I'm going to have the units in EV and nanometer, and about half the class will forget to convert to newtons because I'll say answer in units of newtons in scientific notation just to see who read the fine print. So just be aware that you can get from this to that, and that's useful. All right. I don't want to belabor that anymore. Just try not to screw that up when it shows up. This is that problem. Okay, it's your chance to practice that. Let's get back in there. All right. Okay, so we sketched the plot. You could sketch your own. Ooh, let's do this. Oh, I love it. This is the last question that we haven't tied of this type. So this is kind of the last piece of this stuff. Consider an electron initially located at the bottom of the left potential energy well, at the left minima. What initial speed is required to get to the right? Whoa, let's get this up on screen here. We said, imagine you have an electron sitting right here, and it needs to get from right here to over here. And I said, how much speed do I need? What are we supposed to do? Any ideas? Any guesses? This is a plot of U versus X. And I asked about speed. Do you know anything that relates U and speed? What would you try and do here?
Well, I guess I would go back to the force.
Okay, so we could get from U to force, and then you could do force and kinematics. However, is the force constant?
No.
So that would be very challenging. Do you agree?
Yeah.
Unless you know Python. But we'll work on that in 2 weeks. So, all right, that was a good idea. Do you know any other equations that talked about U, potential energy, and something that had speed in it?
Could we do the energy equations?
You can. We could say U initial plus K initial. Nice job. Plus work something else, external, let's say non-conservative, equals U final plus K final. You could do this. Now, I am going to make an assumption right now that this is the only energy we need to worry about, meaning I'm going to make the assumption that work external is 0. So if we're starting here, how do I get U initial? Give me a number for U initial, approximately, if I'm sitting down here.
So like negative 3.5.
Okay, so this number is negative 3.5 units matter now. I better write them EV, I think we said, right? Yes, EV. Okay. Now, kinetic energy. I'm looking for the initial velocity. So basically, this is the unknown. Agreed? what the heck do I put in for U final and K final? What's your gut tell you? I want to get from the initial spot on the left well over to the right well.
Well, U final will have to be the same as U initial, right?
No, that's
No?
what's weird. Well, okay, once it gets over there, yes, you are right that once it gets to this position right here, it would have the same potential, but that doesn't help me figure out how much energy I need. That just tells me that the initial and final kinetic energy would be the same, but I still wouldn't know what it is.
I guess I would try to find out in the middle.
This is the problem area, getting over the hill. This is where that marble, like, think about this. If you started with a marble right here and you wanted to get over this, we would have to have trouble getting over the top of the hill. Approximately, what is the velocity at the top of the hill if we're just barely able to make it?
So it'll be 0.
So that says this is 0. And what is the final potential energy at the top? 1 EV. And now look at this cool result. We know U initial, we know U final, we know K final. We could solve for K initial and get the speed. And this is a cool trick you could do with these plots. Basically, we could do exactly the same problems as we did to start this chapter with these graphs. What do you think of that? Is that cool or what? Well, I think it's cool. All right.
So wouldn't that be the minimum speed to get to the top of that?
That would be
hill?
the minimum speed. So let's
Okay.
read what it asked. What minimum speed? Yep. So that's the
Okay.
minimum speed. And so we know speeds greater than that, it would make it over there. Now, here's a fun one. Let's get back up there. Let's say we put the electron right here. We have the electron and it's moving with the correct initial speed. Let's just say the initial speed is V min. Okay, so let's say we have the initial speed V min. It's going to get up here. It's going to be almost at rest. So we know that V here is approximately 0. And then what is the marble going to do next? Or what is the atom going to do in terms of its left-right motion? It's going to keep moving. Then what? Where is it going to turn around?
At V minimum?
So do you agree it's going to come down here and it's going to be moving fast again? Once it gets back down to this point, do you agree it'll be back to V min?
Right.
So then is it going to stop at the minimum and turn around? Or is it going to keep rolling past?
It's going to keep rolling past.
How far?
Probably all the way up to 1.
Yeah, until it hits right here. And then it's going to go backwards, right? So at that point, it's going to reverse direction. And then it's going to be right here going this way with speed V min, just like a ball on a track. And so you can think of this ball on a track analogy helps you. Then at the top, it would be, again, V approximately equal to 0, but going slightly the other way. Then it'll get here, and it'll be going this way with speed V min, and then it'll go up to. And this describes the electron going back and forth between these two neighboring atoms. So an electron is shared between two neighboring atoms, all right? And this is it's very, very rudimentary, but it kind of gives you a feel of how you could mathematically model that. That's what I was going for. All right. Here's a subtle question. Where would the electron or the marble spend the most time? Where is it going to be most often?
Where its velocity is almost 0.
Exactly. So if you were doing experiments, right, it would start hanging out in this area and in these two areas a lot. And so it wouldn't be found right near the nucleus that often, even though that's where it would actually have its lowest potential energy, right? And what happens is it's going to overshoot that all the time and just keep flying around. But so it's actually going to spend more of the time away from the nuclei than actually at the nuclei, which is kind of unusual. Now, this is very contrived. This is not a realistic model, but it gets you an idea of many of the things that might happen. And that was a key component in quantum mechanics that you want to think about as you think about, oh, so wherever the potential energy is a maximum, that's actually where the electrons end up hanging out for the most time. That's where they're most likely to be found. Whew. All right. Did we do this one? I think we did. Whoops, wrong button. Oh my gosh, that was crazy. All right. I think we've covered that. I have no idea if this is helping you or not, because this is a tough topic to kind of go through without seeing your faces. So maybe I'll pause for a second and see if there's any. Is this helping? Is this not helping? Do you have questions? All right. No questions is usually a good thing, so I'm gonna hope so. Just don't be shy. If I'm doing a bad job, you got to tell me. You know, I can't tell if you don't know something, so I'm not offended here. All right. That said, that's it for chapter 8.
So
Go
in
ahead.
chemistry, we talk about the uncertainty principle, which
Yes.
says that you can't tell potential, or you can't tell energy and position by exactly, or something like that.
I think you mean momentum and position, but yeah. We talk about that ad nauseum in physics 162. So that's when we do all of the uncertainty principles. We do quantum mechanics. We do special rel. We do all those cool things. For right now, there is an energy relationship. So if it helps, well, let me say it like this and then get out of this question. I'm going to kind of gloss over it, okay?
That's fine.
But H bar is a unit that you've probably heard of, right? H bar is action, unit of action, energy times time. So action is a physics unit. It's old school, even older than me. That's crazy, right? But so if you talk about change in energy versus change in time has to be greater than or equal to, it's either H bar or H bar over 2, depending what you're doing. And let's just say this. And then there's change in momentum times change in position has to be greater than or equal to H bar over 2 as well. And so this is a unit of, well, you can see this is a joule times a second. So H bar is something that has units of joule seconds. And if we do the units on this, it will match up as well. And so great. Momentum is the next chapter. We'll probably start that in about 10 minutes or something, maybe an hour. But yeah, what this is saying is if you measure position very well with a low amount of uncertainty, remember we did labs, right? There's always screw ups in measurements. So the better you measure position, the worse the error is on your momentum. Now, momentum is just mass times velocity. So there's an error basically in your velocity. So you can either know where something is very well or where it's going, but not both simultaneously.
Yeah, there you go. Okay.
Yeah. And then the same thing is true with energies and time. Usually this shows up, energies relate to hc over lambda. Now, or in chemistry, they use h nu for frequency. And this has to do with time. And so that has to do with the line widths of the atomic spectra and how well you can do that. And so basically, the longer time you spend measuring, the more precisely you can measure the energy levels of an atom. Whereas if you use very short times to measure energy levels, the error in those energy levels goes up. It's totally unrelated to what we're doing right now. So let's save the rest for office hours or physics 162. Is that good for right now?
Yeah. Yes.
Yeah. So yeah, by the way, the periodic table in chemistry, N is an energy eigenvalue, right? So you'll talk about this. The physicists, right, organized the periodic table for the chemists because we felt sorry for them. All right. Burn. Ooh, so mean. All right. If a physicist isn't making fun of chemists, they're not doing their job right. Because let's face it, who's cooler in the real world? Chemists. They get good jobs and have a good life, but so we get to pick on them in the classroom. That's what we do. All right. Just jealousy, that's all. All right, let's get back to sorry, I'm wasting your time there. I don't want to waste time. Okay. I'm just going to show you a couple more of these. So 8.27. This one just to make it a little bit easier, I did units of meters and joules so you could kind of get your head around it with these. So I think you could do this one at home, but notice this is showing you like this might be one exam question, let's say, or this would be a variation. They use the same plot, and this shows you two different ways I could ask exam questions. So notice this is one that's talking about velocity, speed, and describe the motion. And this one's talking about forces and that kind of thing. All right, so we see a couple of different ways you could write these. You could do those next. And then we're basically back to here, but there was one more. Here's another one. I don't know if you noticed this, but here's one that we saw before. Or this is the opposite. Notice here I give you the f of x graph and x, and I say figure out the plot of u versus x, right? So this is very similar to what we just did, except remind me, if this is a plot of u versus x, how do I get from u to force? What do I have to do?
Negative derivative.
Negative derivative, right? Okay, and so then on the other one, sorry if I could scroll back to it. Here, I've got a plot of force versus x. How would I get from force to potential energy?
Negative integral.
Negative integral. And so rather than try and remember all that junk, I'm just trying to show you right here. On the back of your equation sheet, I'll try to remain motionless for a second. There's those two numbers. And so you've got this right there. If you ever forget those, just take a look or check the units, right? And so I can remember this one pretty easily. Well, yeah, I just have it memorized. So I guess that's how I do it. I don't know. All right. So that's it. And we should probably, I don't know, does anybody have questions about anything in chapter 8 at all? Let's see if there's some good stuff here. Ooh. Oh, man. These are fun problems. They're fun. All right. Let's sketch out one more before we take a break. Let's try one of the other chapter 8 problems to see if you remember that stuff. So here, let's take a look at this one, 8.29. So a roller coaster ride, negligible friction, car begins at rest from height h above the ground, passes through a valley and over her. Okay, so as each rider passes over the top, we want a normal force equal to half of his or her weight. Oh, thank God. There's a giant pile of used scratch paper at the end to cushion the impact as it flies off the track. Got it. Okay, what type of problem does this look like to you? What types of things do you think we might have to do in this problem? 8.29.
I see circular motion.
Okay, what kind of circular motion? Are we going to do kinematics, or what do you think? Energy, forces? I mean, those are kind of our big three tools right now. We have energy, we have kinematics, and we have forces. I think those are our main three tools at this point, right? Which tools would you use to try and figure out the initial height of the ride? I'll wait for a second and let you kind of think about it.
Well, to determine the height, we would have to do energy.
We'd need to do an energy problem, right? So a U initial plus K initial plus work external non-conservative. I'm just going to be lazy and just call it W. I'm just getting lazy. Okay, so I know I'd have to do that. How do I get, when you see this, what does that tell you you have to do?
FBD.
Yeah. So then you're going to have to do an FBD right here. And that was, I think, what you were going for. And I just couldn't tell because of internet and online and stuff. We know you got to accelerate towards the center. And so that was like your old quiz question from last time, or some of you. And so you could see it just starts building and building and building. We're using chapter 6 in chapter 8. This particular problem, we didn't need to do any kinematics at all. So, but this is going to become more and more common where you have to get 2 or more tools out of your physics toolkit to do things. Sometimes you need to do your vector tools. All right. Like in chapter 7, we had to do the dot product. So we had to use our chapter 3 methods for taking a dot product. And at this point, I think the whole rest of the problem is easy, right? You identify the correct approaches. Then it's just algebra. Obviously, the FBD, I did that quickly, but you would probably have to think a little bit and make sure you don't screw up the directions, because you know if you screw up one arrow in an FBD, the whole problem is usually toast. So it's not like it's you don't have to put some effort in, and it's not like you shouldn't practice, but that was a cool one. All right, I'm going to move on to the next one and just kind of go in rapid fire and just think it through. Let's look at this one. We've got this mass. It's going down a 30-degree incline. We got some coefficients. Work done by friction is absorbed by the molecules of the ramp and the block. Okay. We're going to say that, so the work done by friction changes the energy internal of the blocks and stuff. And then for some reason, I decided to make G equals 10 on this one. I don't know why. There must have been some reason. All right. And so making some plots. What do you think the plot of gravitational energy versus time should look like? Is it going to be flat, going up, or going down? What do you think?
Shouldn't it be flat?
Is your gravitational energy staying constant as this thing slides down the ramp?
That's what I was thinking. That's why I said flat. I guess.
Oh, okay. What's the equation for gravitational energy? mgh. Agreed?
Oh, yeah.
And then the height here is going to be something like x sine theta or something, where x is the distance up the ramp it is, and x is not staying the same. So if this distance here, if I could draw it, is x, do you agree it should be actually going down, right? The gravitational energy is where it correlates to its vertical position. And so as it goes downwards, we expect that U sub G should become a more negative number or closer to 0, or however you want to say it. Is that good?
Yeah.
Do you think it's going to be linear or curvy?
Linear.
Well, take a guess. Do you
Take
think
another guess.
Is this going at constant speed or not? Do you agree you do a force diagram, a free body diagram, and you could solve for its acceleration from that FBD, right?
Mm-hmm.
And we expect to get a constant value for acceleration. If your acceleration is constant, shouldn't the gravitational energy increase kind of as time squared? Or decrease as time squared. So I would expect U sub G to start out big and go down like this, like a parabola. So there's time and there's U sub G. So now here's the deal. I probably wouldn't give this question to you on a test because this would be very time consuming. However, I really think this is an incredible question for kind of seeing, do you remember what these equations mean? And it's really a very good kind of review of a lot of stuff, because we have to think about forces, kinematics, and energy all in one big blob. And that's why I put it kind of towards the end of this chapter. So don't try too hard, but see if you can give it a shot, think. So I kind of did the first one for you. You could try and think through what these others might look like and see if you can guess what should be on these other things here. And hopefully I didn't screw up the solutions, but if you have any questions, you can ask me later. All right, so there's that. But it's kind of sneaky like that. We talked about this one already. Ooh, this is a sneaky one. All right. Let's look at 8.32. Here I don't have any graphs and I don't have any equations. So I know I'm not doing the U equals minus the integral, and I'm not doing force equals minus the derivative of U. So this is an energy problem. What would you do in this problem if you were setting it up? Take a second to read, and let's let somebody other than Esteban kind of answer here. So take a second to read about it, think, and then respond what you think you might try to do in this problem. And my apologies, I really have no clue how this is going over today. So this is an energy problem. Someone other than Esteban, make a suggestion how we might approach it. It's okay to be wrong, and it's okay to try and fail. It doesn't matter. Just if you speak up, you'll probably remember the right answers more. So give it a shot.
So you just write out the energy equation and
Okay.
set a reference point.
What type of, yeah, so reference point. Where do you want to cite your reference point?
I guess we could set it where the spring is.
Yep, that sounds good. So we'll say that's y equals 0. So what's the initial height of the block?
Let's see. Would it just be R?
Yeah, because this is a radius and this is a radius. So this is a classic physics trick. They give you a circle and you have to say, oh, y relates to the radius here. So that's good. All right. What types of energy do we have initially? Do we have gravitational? Yes or no?
Yes.
Okay. Do we have spring initial? Yes or no?
No.
Okay. How about kinetic initial? Yes or no?
And we have no kinetic, or yeah, no.
Okay. What about work external non-conservative?
Yes.
Okay. So let's see. Is there work done by friction?
Yeah, we have friction.
Do we? Oh, at the bottom, you're right. Ooh, I didn't see that at first. I saw the frictionless. So yeah, oh, at the bottom. Okay, so we don't have friction for this part. Agreed?
Yeah.
And so we do down. Oh, good job. So there's going to be work done by friction. What about the work done by the normal force? That's an external force.
I don't know. I maybe.
No, it's perpendicular all the time. Remember that?
Yeah, you're
Work
right.
the normal force, even on the ramp, right? You're pushing this way. You're pushing this way. So the normal force is always perpendicular to displacement, even down here. So, and that's it. Okay. Wait, what about the work done by the spring?
The spring is fully extended, so no.
We're going to account for the work from the spring using energy. So that's why we're not going to do it. Does that make
Okay.
sense?
Yeah.
Okay. So in the end, what kind of, do we have any gravitational potential energy at the end?
No, we don't.
Do we have any spring energy at the end?
Yeah, we have spring and kinetic.
When it says max compression, how fast are you
Okay.
moving when you hit max compression?
It's not moving at all.
Exactly. That's where it stops and reverses direction. So max compression, it went all the way up here and then it's going to turn around and go back. That's it. That's the equation. Isn't that wild? It looks like this would be impossible, but it's just mgr. Now, how do we get the work done by friction?
We can draw an FBD.
Yep. And it would be, there's a spring force this way, there's a normal force this way, there's friction this way as well. So we'll call that friction, we'll call that F spring. There's a normal force, and then there's mg. What's the force to the right that keeps it moving to the right?
There is none.
Exactly. You don't need a force to move to the right. If you already have velocity when you hit the spring, right, it's totally fine to have only forces to the left. And notice, as a result, your acceleration is to the left, but you had initial velocity, so you're still moving to the right and slowing down. And then once you get to max compression, that's the spot where your velocity goes to 0, right? So your velocity equals 0 at max compression. And then, okay, cool. So so I think from there you could get the work done by friction. And so let me get back to the other color. And then the spring final energy is going to be 1/2 kx squared. You're off to the races. You could solve for something, okay? All right. Here's a crazy thing. Think about this weird scenario. Depending on the values here, it's possible that this block could compress and stop. Agreed? Because at this split second, it's not moving. So it's possible it could squish that spring, but then the frictional force could be stronger than the spring and balance it. Or let me rephrase, the max possible friction force could be larger than the spring. And as such, once you get to the max compression, friction's going to switch directions. The spring force is still going to be this way. There's a normal force. There's an mg. And so it's quite possible, depending on if things were just right, that you could actually end up with A equals 0 in the final state, and you actually swing down, compress the spring, and stop. I don't know what the conditions would have to be, but so that I decided to figure them out, and that's what this is for. Okay, right? If it's on the verge of slipping, right, we know that K times the max compression would have to equal the frictional force max possible. And you get this weird result. If this, like if you know K, R, M, and G, this is the coefficient of friction you would need to get it to stop. And it's very, very weird. Oh, you'd also need this radius too. It's a strange, yeah, let's leave it at that. Whoa. I'll say one thing and then we'll get to our break. Let's do a quick summary of chapter 8, just to kind of see what we've learned, okay? And what you're supposed to get out of this crap, all right? This is kind of intense because we've seen a lot of different things. But so one thing is U initial plus K initial plus work done by external non-conservative is equal to U final plus K final. We know our gravitational potential energy equation is mgh, and you have to pick a reference level, right? That was one thing that you always have to do. And then we saw if 2 blocks, you could pick 2 reference levels, etc. We said 2 reference levels was okay. All right. We saw that our energy from the spring is 1/2 kx squared. All right. And then we also saw that we could use the change in potential energy is equal to minus the integral of f sub x dx, which was akin to saying f sub x is equal to minus d dx of u. And then I'm just going to put it here. I don't know. The marble analogy is tough. There's a lot in there. Analogy. So we've seen that this, whoops, let me get this a little bit lower here. And let me scoot back just a hair, rotate, get the glare. The marble analogy is a big deal. And you have to practice with it and think it through and try it and fail and ask me questions to really learn that. And finally, we saw that 1 EV is 1.602 times 10 to the negative 19th joules. All right. And this is just a common unit that we're going to see more and more as we get into smaller scale objects. This is everything we learned in this chapter, but the guts are practice, practice, practice. Because this by itself, if you could memorize this and say it back to me, that doesn't mean you know anything, right? That just means you memorized a bunch of symbols, and it doesn't. If you could do problems, that shows you really understand this. And that's the issue with physics in general, right? It's not enough to just memorize a list of facts. You have to be able to use them and deal with all the weird quirks that come up in word problems all the time. All right. Let's go ahead and take a break. If you have any questions right now, that's fine. And I'll wait just a second to see if you do. But that's kind of chapter 8. I'm going to stop the live stream now, and we'll pick up and start chapter